Welcome to another lecture in engineering mechanics. In this lecture, we will investigate the relationships between loading, shear force, and bending moment. In this lecture, we will examine the relationships between distributed loads, shear forces, and bending moments in beams. We will introduce the differential and integral connections between these quantities and use them to better understand the behavior of shear force and bending moment diagrams. We'll begin by considering two common loading cases for beams. The first beam is subjected to a distributed load, while the second beam is subjected to a concentrated load and a concentrated moment. We will use these loading cases to develop the relationships between loading, shear force, and bending moment. First, we consider a beam subjected to an arbitrary distributed load. To investigate how the internal forces vary along the beam, we isolate a very small beam segment of the length delta x, located at a distance x from the left support. We will now examine the equilibrium of this small beam element. Before continuing, let's briefly recall the sign conventions used for axial force, shear force, and bending moment. We will continue to use the same sign conventions that we introduced in previous beam lectures throughout this analysis. We now draw a free body diagram of the small beam segment of the length delta x. The distributed load acting over this very small length can be approximated as constant. We then apply the internal shear forces and bending moments acting on either side of the element and use equilibrium equations to relate the changes in shear force and bending moment to the applied loading. Notice that the internal forces on the right-hand side of the element differ slightly from those on the left by delta S and delta M. It's important to recognize that this derivation applies only to regions of the beam where there is no concentrated load or concentrated moments. The beam segment is selected at a general point X along the beam, where the loading varies continuously. Since the segment is chosen at a point where there are no concentrated loads or concentrated moments acting directly on the element, the relationships derived here do not apply directly at locations where concentrated loads or concentrated moments are applied. At those locations, the behavior of the shear force and bending moment diagrams changes suddenly, and we'll consider those effects separately later on. We now apply equilibrium equations to the small beam element in order to derive the differential relationships between distributed load, shear force, and bending moment. First, applying equilibrium in the vertical direction, the sum of forces in the y direction must equal 0. And this gives the relationship delta S equals negative W of x multiplied by delta x. This expression shows that the distributed loading causes the shear force to vary along the beam. Next, we apply moment equilibrium about point O. And this gives the relationship delta M equals S multiplied by delta x plus W of x multiplied by Wx squared divided by 2. Since delta x squared is extremely small compared with delta x, the final term can be neglected with insignificant loss of accuracy. And this leaves delta M equals S multiplied by delta x. This expression shows that the bending moment changes along the beam according to the value of the shear force. We now convert the previously derived relationships into differential form. Starting with delta S equals negative W of x multiplied by delta x, dividing both sides by delta x and isolating W of x gives us W of x equals minus delta S divided by delta x. As delta x becomes extremely small, this becomes W of x equals negative ds by dx. This relationship shows that the distributed load intensity is equal to the negative slope or rate of change of the shear force diagram. Next, starting with delta M equals S multiplied by delta x, and again dividing both sides by delta x, and this time isolating S, we get that S equals delta M divided by delta x. Again, taking the differential form gives us S equals dm by dx. This shows that the shear force is equal to the slope or gradient of the bending moment diagram. These are the fundamental differential relationships connecting distributed load, shear force, and bending moment in beams. These differential relationships allow us to directly interpret the behavior of shear force and bending moment diagrams. The first relationship states that the intensity of the distributed load at a point is equal to the negative slope or gradient of the shear force diagram at that point. This means that distributed loading causes the shear force diagram to vary along the beam. The second relationship states that the value of the shear force at a point is equal to the slope or gradient of the bending moment diagram at that point. This means that the shear force controls how the bending moment changes along the beam. These relationships are extremely important because they allow us to predict the shape and behavior of shear force and bending moment diagrams directly from the applied loading. We now build on the relationships for delta S and delta M derived earlier by expressing them in integral form. First, consider the relationship delta S equals negative W of x multiplied by delta x. Integrating both sides gives an expression relating the shear force to the distributed load acting along the beam. This shows that the shear force develops from the accumulated effect of the distributed loading over a region of the beam. Next, we consider the relationship delta M equals S multiplied by delta x. Again, integrating both sides gives an expression relating the bending moment to the shear force distribution. This shows that the bending moment develops from the accumulated effect of the shear force along the beam. These integral relationships are extremely important because they connect loading, shear force, and bending moment through the areas under the corresponding diagrams. These integral relationships allow us to interpret shear force and bending moment diagrams in terms of areas. The first relationship states that the change in the shear force diagram between 2 points is equal to the negative area under the distributed load between those points. This means that distributed loading accumulates to produce changes in shear force along the beam. The second relationship states that the change in the bending moment diagram between 2 points is equal to the area under the shear force diagram between those points. This means that the bending moment develops from the accumulated effect of the shear force along the beam. These area relationships are extremely useful when constructing shear force and bending moment diagrams, since they allow us to determine how the diagrams evolve between different points on the structure. We'll now consider beams subjected to concentrated loads and concentrated moments. Unlike distributed loading, concentrated actions act at specific locations along the beam, and therefore they produce sudden changes in the internal force diagrams. To investigate this behavior, we isolate a very small beam segment of length delta x at the point where the concentrated load and concentrated moment are applied. We will now use equilibrium equations to determine how the concentrated loads and moments influence the shear force and bending moment diagrams. We now apply equilibrium equations to the small beam segment containing the concentrated load and concentrated moment. First, applying the equilibrium in the vertical direction, the sum of forces in the y direction must equal 0. This gives delta S equals negative P. This relationship shows that a concentrated load causes a sudden jump or change in the shear force diagram. The magnitude of the jump is equal to the applied load, while the sign depends on the chosen sign convention. Next, we apply moment equilibrium about point O. This gives an expression involving the applied concentrated moment together with several terms containing delta x. Since delta x is extremely small, the remaining terms involving delta x can be neglected with insignificant loss of accuracy. And this leads delta m equals negative m sub c. This relationship shows that a concentrated moment causes a sudden change or jump in the bending moment diagram. Again, the magnitude of the jump equals the applied moment, while the sign depends on the chosen convention. We can now summarize the differential relationships for concentrated loads and concentrated moments. Unlike distributed loads, concentrated actions act at a single point rather than continuously over a length of the beam. For this reason, we do not integrate these relationships in the same way we did for distributed loading. Instead, concentrated loads and concentrated moments produce immediate changes or jumps in the internal force diagrams. The first relationship shows that a concentrated load causes a sudden jump in the shear force diagram. The magnitude of the jump is equal to the applied concentrated load, while the sign depends on the chosen sign convention and the direction of loading. The second relationship shows that a concentrated moment causes a sudden jump in the bending moment diagram. Again, the magnitude of the jump is equal to the applied concentrated moment, and the sign depends on the chosen sign convention. Unlike distributed loading, concentrated actions therefore produce instantaneous changes in the internal force diagrams at the exact point where they're applied. We can now summarize a practical procedure for constructing shear force diagrams. The first step is to determine the support reactions using equilibrium equations. Next, we establish the shear force and beam length axes and plot the known shear force values at key points along the beam. The behavior of the shear force diagram can then be determined using the differential and integral relationships developed earlier. The slope of the shear force diagram is related to the distributed loading, while changes in the diagram are related to the area under the load distribution. Distributed loads, therefore, produce a gradual variation in the shear force diagram, while concentrated loads produce sudden jumps. These relationships also allow us to predict the general shape of the shear force diagram directly from the type of loading applied to the beam. We can also summarize a practical procedure for constructing bending moment diagrams. First, we establish the bending moment and beam length axes and plot the known bending moment values at key points along the beam. The behavior of the bending moment diagram can then be determined using the relationships developed earlier between shear force and bending moment. The slope of the bending moment diagram is controlled by the value of the shear force, while changes in bending moment are related to the area under the shear force diagram. As a result, the shape of the bending moment diagram can be predicted directly from the behavior of the shear force diagram. Concentrated moments produce sudden jumps in the bending moment diagram, while distributed loading causes the bending moment to vary continuously along the beam. Thank you for joining me. In this lecture, we developed the integral and differential connections between loading, shear force, and bending moment in beams. This will allow us insight and help us construct the diagrams for shear force and bending moment more effectively.